In this video we look at another type of flip-flop that's called an edge trigger D flip-flop, and the edge trigger D flip-flop is a more sophisticated flip-flop than the RS flip-flop. One reason it's more sophisticated is because there is no ambiguous state. If you look in these two truth tables, and we'll talk more about these truth tables coming up, but first just notice that in all the possible rows of each of these truth tables for the edge trigger D flip-flops, not Q is always the opposite of Q. So you never have a case where the Q outputs are the same. So that's one advantage the edge trigger D flip-flop has over the RS, is that there's no ambiguous state. Also, the edge trigger D flip-flop can be easily synchronized, and I'll talk about what's meant about what synchronization is and why it's more easier to synchronize with edge trigger D flip-flops than RS flip-flops in a later video. But what I have here are the symbols and also the truth tables of the two different types of edge trigger Ds. This one here is called a positive edge. A positive edge, or leading edge. Okay, so two names for the same type of edge trigger D. And I'll be using both of these in the course. This type over here is called negative edge. Okay, and it is also referred to as trailing edge. Now notice in the symbols, the only difference, the only distinction between the two symbols is that the negative edge has a little bubble on the clock input. See the inputs of an edge trigger D, one input's called the D input, which is short for data, and then the other input is CLK, which is clock. Notice that it has this little triangle, and we'll talk more about what's meant by the term clock in just a moment. Okay, but just like the RS flip-flop, and for any flip-flop for that matter, the outputs for the edge trigger D flip-flop are Q and not Q. Okay, let's look at our truth table, and you all know what zeros and ones are. We've seen those in truth tables before, but what's new in the truth table of the edge trigger D are these arrows. For the positive edge or leading edge, the arrow is pointed up for the clock input, and for the negative edge or trailing edge, edge trigger D, the clock in the clock column, the arrow is pointed down. Well, what these arrows refer to are clock transitions. So the upward arrow is referring to the time the signal on the clock input goes from a 0 to a 1. Okay, so it's talking about the time at which this transition occurs. And then the downward arrow is referring to the time that a 1 to 0 transition occurs. Okay, on the clock input. Okay, so upward arrow is this time, downward arrow is this time. So you see what this truth table is telling us is that if our D input is equal to 0, at the time of the 0 to 1 transition of the clock input, well, Q will be 0 and not Q will be 1. If D is 1, at the time of that 0 to 1 transition of the clock, well, Q will be 1 and not Q will be 0. And for the edge trigger D, the negative edge trigger D, it's the same thing, except the output Q is going to equal the input D at the time at which the clock signal goes from a 1 to a 0. So the way that you can summarize the operation of either one of these edge trigger Ds is that output Q will equal input D only at the time of the appropriate clock transition. Okay, and what I mean by appropriate here is that, well, if it's a positive edge, it's the time of the 0 to 1 transition. If it's negative edge, it's the time of the 1 to 0 transition. So you see, except at the time of the appropriate clock transition, the Q output will always remain what it was previously, because it only has the possibility of changing and equaling what the D input is equal to at the time of the appropriate clock transition. So what this means is that this type of flip-flop is storing data at all other time other than the appropriate transition of the clock. So you see here for the positive edge, for all other time other than the 0 to 1 transition of the clock, this flip-flop storing data, because Q is going to remain what it previously was. It only has the possibility of changing to what the D input is on this 0 to 1 transition. And everything that I said for the positive edge is true for the negative edge, except Q output can only possibly change on the 1 to 0 transition. Well, a good way to see if you understand the truth table of a flip-flop is to look at a timing diagram and see if you can make sense of the timing diagram. So here's a timing diagram of an edge-triggered D flip-flop that's positive edge. Okay, so if you look down here, this is a positive edge. So that means the 0 to 1 transitions are the transitions that matter. So that's why you see these dashed lines on every 0 to 1 transition of the clock input. And then here's our D input, and then you can see that only the Q output is shown, that not Q is not shown. And this is typical for flip-flops like this, that often in these timing diagrams they'll only show one of the outputs. And the reason for that is because there's no ambiguous state with this type of flip-flop. Well, not Q is always the opposite of what Q is. Okay, so it's just understood that not Q is going to be the opposite of what's shown here for Q. Now notice that all the values here start at 0. That was just arbitrary. It had to start, these inputs are digital binary, so they have to start either at 0 or 1. So the person that made up this timing diagram just decided to make all the initial values 0. But there's other timing diagrams where the initial values are 1 instead of 0. So there's nothing special about these all starting at 0. Okay, but let's see what happens as time progresses. In these timing diagrams, time progresses as you go left from right. So t equal to 0, our input D is 0, clock is 0, and also output Q is 0. Well, the first thing that changes is the D input goes from a 0 to a 1. And at the time that the D input changes from a 0 to a 1, notice the clock is just low, it's just at 0, and notice that Q stays what it was previously, it stays at a 0. So you see at this time right here where the D input went from a 0 to a 1 and Q remained the same value, storage of data just occurred right there. Okay? See, it's not until this first 0 to 1 transition of the clock comes along that Q is going to change, because anytime there's a 0 to 1 transition for a positive edge trigger D, that's when output Q will equal input D. So you see, that's why you see the Q output change from a 0 to a 1, because it equals D, which is a 1 at the time of that 0 to 1 transition of the clock. Okay, continuing on in time, when the clock goes from 1 to 0, you can see the Q output just stays the same, and that's because since this is a positive edge trigger D, the negative edges of the clock, the 1 to 0 transitions, are irrelevant. Okay, they're not going to have any effect. Okay, time progresses on. You can see the next thing that happens is D input goes from 1 to 0, but at that time the Q output stays 1 because, again, there was no appropriate clock transition, so storage of data occurred. And then you can see here that the Q output will go to 0 when D equals 0 on the next positive edge of the clock. So understanding a timing diagram like this is usually a good indication that you understand the truth table of a flip-flop, and if you understand the truth table, then you know how the flip-flop works. Now, we'll be talking more about flip-flops in upcoming videos. As I mentioned, I'll talk about what synchronous means in a future video coming up, and also we'll talk about JK flip-flops, which are also edge triggered type devices, And that will lead us into devices made out of flip-flops, namely counters and registers.